I hope you find this review helpful. As most of your teachers, I want you to do well on your exams, so we'll see. Um, it's broken up into, this really should say chapter 1. So what I've done is just to bring in some slides from class. And one of the questions is going to be with regard to probably something along the line of physical sciences, which is not a physical science, probably be a multiple choice question. So some things I know what the questions are going to be, sometimes I don't. I'm also going to have a question. It could be multiple choice or it could be short, or excuse me, it could be fill in the blank, but I think it's important that we differentiate between hypothesis and theory. Remember, hypothesis is best guess, sort of, and a theory actually then is after that hypothesis has been tested and found to fit the experimental data. Then it can be elevated to a theory. So kind of know that. I introduced the term pseudoscience, and a pseudoscience just probably ends in ology, the suffix ology, and it's not a real science. So examples of those, I said, for instance, pseudoscience, it's not a real science. And I'm going to have hallmarks of science coming up. So for instance, these guys are pseudosciences: ufology, astrology, numerology, parapsychology. They're interesting and fun, but they don't follow the scientific method, in that we cannot predict with accuracy, make predictions based upon how they behave. So hallmarks of science, and this probably be a multiple choice sort of question, science needs to explain observed phenomenon, and their explanations need to be explained by natural causes. Let's see, this one right here. It needs to be as simple as possible, the explanation. This is the keep it simple, stupid. Another hallmark of science, like I said, that's where some of these pseudosciences don't make it, is that your science needs to be testable. So, yeah, hallmarks of science. Then there are 4 metric prefixes I want you to know. They are kilo. Where is kilo here? Yep, kilo is the only one that actually is large. So it's 1,000 times the base unit. Then I have 3 small ones. So centi is 1/100th, milli is 1/1000th, and micro is 1/1,000,000th. Okay, the symbol for micro, I don't know why they did this, but the symbol for micro actually is this letter right here. It's called mu. And of course, the symbol for milli is a lowercase m, the symbol for centi, c, the symbol for kilo is k. So know those 4 metric prefixes and what they mean. And then you're going to have a question. I don't know if it's multiple choice or short answer, but I'm going to want you to pack up numbers. So for instance, if you have a large number, you're going to move the decimal place. It's kind of implied over here. You're going to move the decimal place, what, to the left. In this case, we're going to move it 3, 6, 9, 10 places to get 1.23 times 10 to the 10th. All right. And then down here, we're going to move the decimal place over here to the right, and let's see how many places we're going to move it. 1, 2, 3, 4, 5, 6, 7, 8. We're going to move it 9 places to get a number 4.721 times 10 raised to the, it'll be the -9th. Okay. Oh, naked number alert. So this is kilometers. Okay. And this is seconds. So no naked numbers. All right. So be able to do that, and probably ask you a question about this. And then we're on to chapter 2. So we started talking about chapter 2, what is a force? And a force is a push or a pull. These are all examples of forces. There are forces all around us. Here in a minute, I have a vocab word that's probably going to be a vocab word on your test. Net force is like the resultant of all the forces as they work together. So units of force are newtons, and newtons can be broken down into kilograms, meters, per second squared. So if on a test you have to come up with, do a force problem, I'm really going to be making sure you include units as you work the problem and in the end. So keep that in mind. Very good. So this is net force, and again, this might be a vocab word or a multiple choice word. And here we have two forces that are equal. Notice that you can kind of see that we use vectors to indicate forces. So the length of it indicates the magnitude or how the strength, and the direction of the arrow indicates the direction of the force. So here actually your force is actually stronger this way, so you can see that the net force actually is this way. This one has no net force. Okay, because they're equal in opposite directions. One of the things we talked about was speed, just simply speed, and you probably already have a good fix on speed. Later, actually, we're going to kind of quickly change from speed to velocity, but they are different. Speed is the magnitude, and velocity is the magnitude or how fast and the direction. So speed, you just simply take distance divided by time. And I went ahead and introduced this, and actually your textbook does too. Oops, there it is. This idea of this triangle means change in distance divided by change in time. So we did this example where we came up with the speed of this car at different intervals, and it was moving, I believe, the same speed. Okay. So in this case, let's see. So on the previous slide, we came up with the speed is 20 meters per second. Now remember, if you're going to work this in the problem, I really would go 20 meters per 1 second. That's what that means. In this case, now we're going to work a couple of problems using speed. I'm not going to finish working them. I'm going to set them up for you. How far does it travel going at this speed in 2.5 seconds? How I work it, and I saw you guys work it on your homework, is I put 2.5 seconds over 1 is my first term. And then I look at this to see how I can use my speed to get seconds to cancel. I'm going to use it just like that, 20 meters per 1 second. And then seconds cancel. See what I mean? We're going to round to just one digit. This one is how long will it take in seconds to travel 136 meters. So working this sort of problem, I'm going to put 136 meters over 1 as my first term. And now when I go to use my speed, notice that I need to flip it. I need to put 1 second over 20 meters so that my meters will cancel. Okay, and I'm left with units of seconds. Again, we just kind of round it to one digit. And units here will be seconds, units here will be meters. So make sure as you work the problems you include the units. And rounding, if rounding's going to throw you off, I'd rather you not worry as much about rounding as making sure you write the right number. I mentioned speed. Speed is change in distance divided by change in time, and then velocity then adds direction. Okay, so there we go. So velocity then, if you change the velocity, you have what we call acceleration. We kind of talk about our cars have an accelerator, so we give it gas or take away some of the gas. We give it gas, we speed up. We take away gas, we slow down. So any of these is a change in velocity. For instance, if we increase our speed, if we decrease our speed, or if we move in a different direction. And then I kind of made sure that we're all on the same page. If something is moving in an arc or something is moving in something other than a straight line, then actually it is accelerating because it's changing direction. So for instance, we said the car is here, here the car is here, here the car is here, here the car is here, so it's definitely changing direction as something goes around a circle. So here are these acceleration problems. So acceleration, just symbol A, sorry, is change in velocity divided by change in time. So a car travels due north beginning from rest. So hopefully you're okay with that. Means that its initial velocity is 0 meters per second. And then in 3.4 seconds, so that's the change in time, it's now traveling 15 meters per second. Well, if it went from 0 to 15 meters per second, then its change in velocity must be what? 15 meters per second, right? And I already said that its time, change in time, is 3.4 seconds. So here's where we can go ahead and set up our acceleration problem, and it'll be 15 meters per second divided by 3.4 seconds. Now, I'm not going to do that for you, but you get 2 sig figs. And remember now, the units are meters per second squared. That's what the units of acceleration are always going to be. Length per time squared, or meters per second squared. And I'm not going to do the second one. I think you'll be fine with that. On to chapter 3. So I'm going to ask you questions. I can't decide what's going to be multiple choice, or some of this might be, I guess, vocab, and then actually maybe even short answer. Newton's 3 laws of motion. So his first law of motion is called constant motion, basically. It means that if you're at rest, you're going to stay at rest. And if you're in motion, you're going to stay in motion in that same motion unless acted upon by an outside force. So you can change motion, but that means that another force has acted upon you. So here we have, sometimes it's called the law of inertia. So for instance, these coins at rest, if I move this quickly, the coins are going to want to stay at rest. And, if you're fast enough, the coins will stay there when you move a piece of paper. Inertia, those things aren't moving, right? They're okay. Here's some things with moving. So for instance, this was, kind of I think interesting. So this is the guy, he starts here, and the bus moves, but of course he's got a certain amount of inertia for being where he is. So even though the bus moves, he wants to stay where he is, so he falls back. And in this case, the bus has been moving, and then the bus stops, and he doesn't get the memo. He's still moving in the forward direction as the bus stops, and so he falls forward. So anyway, we talked about inertia, and as it turns out, inertia, the tendency for an object to want to stay in motion if it's already in motion, or stay at rest if it's at rest, is relative to mass. So here I have mass 1, and here I have mass 2. Of course, the guy is heavier than the little girl, and so actually this guy has more inertia. All right. Newton's second law. I know all my slides say 3 laws, but this is second law. Force is equal to mass times acceleration. I told you I usually think of the force applied, and it results in a certain acceleration. And the acceleration it results in is actually a function of the mass as that thing is accelerating. Okay, so that's his second law. Third law is for every action, there's an equal and opposite reaction. For every action, every force, there's an opposite and equal, opposite and equal and opposite force acting upon it. So I have some examples here. It's Newton's third law. So know his 3 laws. Newton's general law of gravitation. Okay, here is the equation, and remember that actually all objects, I don't know if I have a slide here, but all objects have an attraction towards each other. This is M1, this is M2, this is the R, or the distance between them. And the pull of the gravity, the attraction they have for each other, is you take the masses, divide by the distance squared, and then you multiply it by this gravitational constant. So we said then, so that's what the variables stand for, and we said that if you increase R, you increase the distance between them, hopefully we're all on the same page, you would imagine that the force of gravity would decrease, and you're right. If you increase the masses, the force of gravity increases, and you're right. Cool. Yeah, this is what I kind of drew over there. Now, just talking a little bit about mass. Now, mass is universal. Mass is kind of related to the number of atoms and kind of how much the atoms weigh. How much mass the atoms have, excuse me. Weight then goes back to the force of gravity. Weight actually is the force of gravity. And weight can be calculated by taking the mass that the object has times the acceleration due to gravity. Little g is that 9.8 meters per second squared. And I don't mean to confuse you, but it is. So the weight on Earth, okay, the g is 9.8 meters per second squared, and actually g, the constant of things accelerating on the moon, then actually would be about 1/6 times 9.8 meters per second squared. Okay, bottom line is that your, like this says, your mass on the moon and the Earth would be the same. Your weight would be actually about 1/6. Darn it, 1/6 of the weight on the moon as you weigh on the Earth. Okay, so one of the things that actually we watched a little video, and on the moon, the Apollo mission, one of them dropped a feather, and actually it was a hammer on the moon, and they hit the moon at the same time. Okay, the surface of the moon at the same time. And the reason is kind of like this. This is a vacuum, okay, and there's no air particles to give air resistance. So actually, objects will accelerate, whether it's on the moon or the Earth, at the same speed, regardless of their mass, assuming there's no drag due to air particles. So acceleration, we are going to use the acceleration due to on Earth is 9.8 meters per second per second. So every second it falls, it will go 9.8 meters per second faster. So that's why it looks like that. So for instance, we talked about this. In the first second, an object will be going 9.8. The second, it's going 2 times 9.8. In the third second, it's going 3 times 9.8. And you can double check this is the case. In the fourth second, it's going 4 times 9.8. Now, one of the things I fussed about is I don't like it didn't really kind of show these distances correctly, because it will fall farther and farther during that 1 second period for each second it falls. Cool. So if you're going to, we can use this equation, and I think I'll probably just kind of stick with this equation, where we assume then that the initial velocity is 0. Okay, if the initial velocity is 0, then we can calculate the final velocity of a falling object this way, or moving object. It doesn't have to be falling, it could be moving horizontally. So the final velocity of an object is the acceleration that the object is undergoing times the time over which that acceleration is occurring. So for instance, if a car is accelerating at, now this would be horizontal, not vertical. The car's not falling, it's actually just moving, going faster and faster. 5.41 meters per second. How long in seconds will it take? So I'm after, in this case, I'm after t. How long in seconds will it take to be traveling, this is my final velocity. So to be traveling a final velocity of 22.4 meters per second. We talked about this. If I'm after t, so do you see where my final velocity is this, my acceleration is this, and I kind of encourage you to go ahead and write these out. If I have this and this, and I'm after this, I'm going to rearrange this by dividing both sides by the acceleration. So here I have the time, almost the temperature. I have the time is equal to the final velocity divided by the time. Oh, sorry. Final velocity divided by the acceleration. So I'm going to set this up by, I'm going to say time, and we're going to see if our units make sense, is equal to the final velocity, which is 22.4 meters per second, divided by the time, which is, oh, sorry, darn it. Final velocity divided by acceleration. We said the acceleration is 5.41 meters per second squared. Okay, unit-wise, do you see where this meter cancels with this meter? And as it turns out, I have units of seconds squared. Sorry, I have units of seconds and seconds squared. So one of these cancels, and I'm left with actually one of these is left. So unit-wise, I have, it looks like this. Okay, do you buy that? Well, I don't know if you do or not, but in that case, actually, as it turns out, if you have something in the denominator of the denominator, we can go ahead and resolve that into simply the numerator. So it just is, trust me, This is how the units cancel. So we're left with units of seconds, which is perfect. So if I literally divide the 22.4 meters per second divided by 5.41 meters per second squared, I will get units of seconds, which is awesome. And I'm actually allowed 3 significant figures here. So take a look. All right, now on to chapter 4. And chapter 4, we talked about work, and actually you did a lab like this. Remember, you carried those books up a certain distance. In this case, this isn't vertical work, and actually on your lab I called it horizontal work. Sorry, in the lab you were doing vertical work. This actually is horizontal work. So we're pushing horizontally. Now, in this case, the work accomplished is equal to the force applied times the distance over which the distance that the object is moved. So here the distance is equal to 0. Okay, so then if you put a 0 here, of course you get 0 work. Okay, so this guy, he's not accomplishing anything. This guy over here, actually, we can see him apply a force, and he is relocating that object this distance. So all we have to do to get work is to take the force times the distance to get the work. Now, I'm all about units in here. Of course, units of force, you would hopefully tell me, are newtons, and units of distance, we're going with meters. So you could go ahead and give the units as newton meters. That would be awesome. The other thing about work, and actually energy, we're going to talk about in a minute here, is they are the same thing as joules too. So newton meters or joules are the same thing. The other thing, and I don't mean to throw you off, but if we were to go ahead and break a newton down, we would get kilogram meters per second squared, and we combine that with the meters, we get kilogram meters squared per second squared. So all 3 of these are perfect units for work or energy. So for instance then, let's kind of take a look. In the figure above, he pushes a crate with a force of 2.5 newtons, a distance of 6.12 meters. So force is equal to 2.5 newtons. Okay, distance is equal to 6.12 meters. Okay, so if we're just using that formula, so all I got to do, don't make it harder than it is take work is equal to 2.5 newtons times 6.12, sorry, hopefully you can read that, 6.12 meters. Okay, I'm going to give myself 2 sig figs. Units, we could either put joules or newton meters. They're just both perfect. Okay, so yeah. Now this would be work against gravity. This would be the vertical, I can't spell vertical, sorry, the vertical work. Okay, and in that case we actually are working against gravity. So the force then is, the force here is going to be this force here. So the force is equal to the mass of the object that we're lifting, or that's being dropped, I guess. The mass times g, and remember g is that 9.8 meters per second squared. So now if I plug this in for this, okay, I would get work is equal to the mass, g, and d. And instead of d here, we put h. So that's kind of how that goes. The height that it's relocated, it's the same thing. So an example of that we did is this, where we know the mass of these. Mass are 9.07 kilograms. And we know that we are going to relocate them a distance of 1.52 meters. And so we're supposed to knock out what work is done. So we're going to use this formula. This is vertical work. And so we just string them up. 9.07 kilograms times, let's see, g, 9.8 meters per second squared, times h, 1.52 meters. Notice that here's where the units could either be, we're going to give it what, 2 sig figs, and units could either be kilograms meters squared per second squared or joules. Okay, and with regard to how much energy was expended, actually energy is the same as the amount, the energy that is expended is the same amount as the energy or work that is accomplished. So energy, we talked about different forms of energy, and I don't think I must have a test question over that, but we did talk about potential energy is stored energy, kinetic energy is energy being spent. Units of energy are joules, and remember we said joules could be Newton meters or kilogram meters squared per second squared. Okay. So to knock out the kinetic energy, this is a nice little equation to do so. So kinetic energy, we just take we take the mass of the object, we take the speed it's going, we square it, and we take that times 1/2. So in this case, what is kinetic energy that has a mass of 7 kilograms and has a velocity of 13 meters per second squared? So remember we set this up, KE is equal to 1/2. And I'm going to want to see you write this work down. Don't just throw it in your calculator. Write the work down. You'll have plenty of time, including the units. 1/2, 7 kilograms times 13 meters per second squared. So if I focus on the units, that's why I get units of kilograms, meters squared per second squared. And I'm only going to give it just 1 sig fig. Again, if you're queasy about giving it 1 sig, go ahead, sig fig, go ahead and give it 2 if you want to, but I want you to get the right magnitude of the problems, more important, okay? All right, so potential energy, the potential energy I talked about was that with regard to being able to fall to the earth. So we have this kind of thing going on. It has more potential energy the higher it is. So then related to that, we could come up with the potential energy, PE is equal to mgh for this cute little apple, where the mass is 0.14 kilograms, the height is 1.2 meters, and hopefully we're okay with g is equal to 9.8 meters per second squared. This one actually talks about how if something up here, this person released a rock up here, it had the most PE and the least KE. Hope that makes sense. Kinetic energy was the least because it wasn't moving, okay, before he released it. And then actually as it falls, it's decreasing. So when it's down, PE, so down here, it basically has no potential energy because it has no distance above the ground. And right before it drops, it has the most speed, so it has the most kinetic energy. Related to that, up here, if you think of a pendulum kind of swinging back and forth, okay, when it's here, it's fastest. And if it's fastest, we know it has the most KE, okay? And up here, it's the highest, so up high here it has the most PE. And actually as it swings through at any given time, we can add its potential energy and its kinetic energy and it will be equal to a constant. I think that is so fun. Speaking of fun, on to the last chapter where we talked about 2 types of waves, and they have things in common, right? We have this wave, which actually is light, and I'll just put light, but you know really that's EM radiation, all the cousins and all that, and sound does this, okay? They have peaks, okay? This is a peak, 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 and between the peaks we have what we call wavelengths, okay? Wavelengths. So I hope we're okay with that. Transverse wave, the particle displacement is at a right angle to the direction the wave is moving. Here the particle displacement is actually in the direction that the wave is moving. Frequency is an important thing. We use the variable f. Frequency then is the number of cycles per second. Okay, and it's amazing because 1 second isn't very long, but the number of cycles per second. So if something is 65 hertz, that means that there's 65 peaks that pass 1 point at 1 second, which is actually kind of low. I just think that is so cool. There's an important relationship between how fast, V is velocity, and it would be in units of meters per second, how fast a wave is traveling relative to the wavelength, and that's meters, and the frequency, that's per second, okay? and it's this. Velocity is equal to wavelength times frequency. So we actually can rearrange that depending upon what variable we're after. So we did some problems, and this works with sound and light. In this case, consider sound wave traveling at this. And if you don't know its velocity, look at the units. Velocity is meters per second. And it gives us, this is the wavelength, and we're supposed to knock out the frequency of the wave. Now, I am good or bad, I don't know. I always have to kind of go back to my core and solve for my my variable. So if I'm after frequency, frequency is equal to velocity divided by wavelength. I'm not going to do it for you, but hopefully you can just kind of plug in velocity divided by wavelength. Now when we do that, actually frequency is going to be in units of what? Per second. I think that's the next one is similar. There is going to be a test question or two, maybe multiple choice, maybe vocabulary, asking you about kind of how this works. So with regard to sound, our audible range in general, and it changes as we age, trust me, is 20 cycles per second versus actually 20,000 cycles per second, 20 kilohertz. If it actually has a shorter frequency, shorter wavelength, higher frequency, so this would be higher F, okay, shorter wavelength, would be ultrasonic. Down here, infrasonic, this would be a longer or a lower frequency, less cycles per second, and this would be a longer wavelength. Okay, so anyway, ultrasonic versus infrasonic, kind of know generally how that would work. I think I did one of these. So these all look like we're kind of rearranging this, okay, to get what we need. Again, this is rearranging this, okay, to get what we need. Yeah, I guess just a couple other things. One is this Doppler effect, and here we see this red car moving in this direction and it's honking all the way. If your person over here, as it passes, you're going to hear this is going to be a higher pitch. Higher pitch means a higher frequency.
I'm ready, baby.
Okay, and this would be shorter wavelength, and this is going to be a lower pitch, a lower frequency, and a longer wavelength, okay, as it passes. So yeah, I hope that was helpful, and best of luck on your test.